Thank you. Welcome to the last presentation of the day before the keynote. You probably are very tired, and I have 173 slides to present about a very interesting topic. EFI, so let's start. It's my second Code Blue. I was here last year, so you probably, few of you know me. I'm a very famous, or semi-famous macOS hacker. I like a lot of stuff. I'm an economist. I like politics. If you follow me on Twitter, you'll see many times ranting about politics. And these days I work for that company, Sentinel-1. It's a next generation AV company. I developed with another colleague the first version of the Mac product. These days I'm just doing random research and helping the developing team because we have a development team. And they have the problem to develop the product, and I just say it's broken or help them develop new techniques. Just a quick note for the translators. Thank you, El Kentaro, for translating the slides to Japanese, and the live translators who have hard work with me because I talk too much. So thank you very much. What is this presentation about? I want to introduce you to EFI. I don't know how many of you know EFI. It's not a topic that many people do research on or know about. And the main core of this is how to teach you to reverse EFI binaries. Many people think it's very difficult to reverse this stuff because it's very low level. What I want to show you, it's not that difficult. As long as you can reverse engineer Intel binaries, you can reverse EFI. And then to terminate, I want to show you how to search for EFI rootkits, some techniques. There aren't many EFI rootkits. One of the reasons, as I will conclude, is no one or very few people are looking for them. And if you are not looking, you will not find anything. Assumptions of this presentation. My research machine was that computer, a MacBook Pro Retina 10.1. This means if you try with different machines, you'll see some small differences, but everything is more or less the same. As long as you find out what those differences are, you'll have no problem with that. I only care about 64-bit operating systems from macOS. The thing is, 32 bits is dead in terms of Apple, so I don't care about that. And also the Sandy Bridge or newer chipset. This means that, for example, Core 2 Duo machines, I'm not interested. I will show you why. Those machines are basically breakable. They are not secure. So if you use those machines, just buy a new one. So why EFI? Why I'm doing this presentation? Why I wrote 173 slides about this? Why it's important? Why I want to show you, to convince you this is an important topic. EFI is a replacement to BIOS. If you are working with computers for the past 30 years, 20 years, in some point in time, you had BIOS. These days, it's EFI or UFI. UFI is a new branch, a new version of EFI because Intel developed the first version until version 1.12. Apple forked the version on 1.10. By forking, it means most of the stuff is there. If you read the documentation from Intel on that site, you can understand everything from Apple. And then Apple has some very specific stuff that I will show you some things. Some of those things, and the others are not very important or something you can reverse easily. So UFI is the new version, is the one that you find on normal PCs. You don't find that one on Macs. If you can talk EFI, if you can understand EFI, you can understand UFI. There's new features mostly, but you can interchange between the two versions. And that is the website. And the first one, you have all the documentation, original documentation. So if you read the first documentation, you can understand UFI, and then if there's something specific, you can move between the two versions. Why is the EFI very important? It's the first component, or one of the first components when you start your computer. The first instruction that your CPU will execute is in a fixed position in the BIOS. So it starts your machine. If you control the BIOS, you start controlling most of the machine because everything comes up after the BIOS. It has access to all the hardware because it will need to talk to the hardware, to the memory to start the machine. It is very modular. You'll see that everything is a module. So it's very feature-rich and modular. You can, for example, you can have an HTTP server. There's a new standard that wants to boot the image of the machine from HTTP. Why HTTP and not HTTPS? That's another discussion. It's very easy to develop. You do it in C. You have two SDKs, Tiano Core and EDK2. They are the same with some differences. Doesn't matter for now. But it's very easy to develop. You just need to know C, some very specifics about the development. And because it's modular, you can develop a lot of modules that will work in all machines that have EFI or UEFI. Before, with the BIOS, this wasn't true. Most of the stuff was developed in assembler. Most stuff was specific to machines. So the development was a lot more complicated than EFI. Interesting things, attacks on EFI, examples of what we can do, why EFI is important. You can build a rootkit that never touches your hard disk. This is very interesting because if you touch the hard disk, you can have hard disk forensics. You just need to have an image of your hard disk. If someone changes a bit in your hard disk, you can detect if there is something that modified, usually a rootkit. So the idea is you put the rootkit data in the flash chip where the EFI is. When the machine starts, you patch something, the kernel, the browser. You can attack the browser, for example, and you never put information on the hard disk. This is very interesting in terms of detection because nothing will go to the hard disk. If you want to more details about this, you can check the Snare's Syscan presentation, where it shows the technique to patch the kernel, to attack the kernel from EFI, and then after that you can do whatever you want against the operating system. This attack can be very hard to detect. As I told you, you are starting at very early in the machine, so you control hardware, and then you have an operating system on top of the hardware. So if you control the hardware and you try to detect something from software, this is very difficult to do. My position is that it's impossible to do. Unless you have an assistant from hardware, a very safe channel that allows you to communicate this. If you want to see a discussion about this, I was discussing this week or last week on Twitter with a few more guys about this because there was a volatility developer saying he could detect this. And we were trying to prove that if you are from software, it will be very difficult to detect something at hardware. More things. You can persist across operating system reinstalls. This would be, for example, a very interesting feature for APT. This would be real APT because if the user you have a Windows installation. You have some malware. As you saw on TT's presentation, you can disinfect the machine, or he told you that it could be very difficult. For example, this would make a very big obstacle to clean the machine because you will reinstall the machine and the rootkit on EFI would install itself again. So you will never clean the machine unless you clean the flash chip. One example of a rootkit from this is Hacking Team. As you know, they were hacked 2 months ago or something, and they had this kind of rootkit. They wanted to, if the victim or the target was infected with this, he could reinstall Windows as many times as he wanted, that he will always be under control of the rootkit from Hacking Team. More interesting stuff. How to attack full disk encryption. You encrypt your machine. If you've been following on Twitter, Stefan Esser says he was attacked this week. Someone broke into his hotel and tried to copy the hard disk. If you have your hard disk encrypted, that will do and not do anything because you missed the password. What you can do you install a firmware rootkit, an EFI rootkit, and you get the password. Many attack scenarios are possible on this. You can have a rootkit that always gets the password, or you can have, for example, a rootkit that you install once, you get the password, and you find a way to send the password to a remote server or something, and then you remove the rootkit. The next step, you go to the hotel, you copy the hard disk, hopefully the password is the same, and you can decrypt everything. So this is a very interesting attack scenario for people that travel, and the rule is never travel with important information, or travel with the least important information you can do. Attack an operating system, I'm not sure if you know Tails. Tails is an operating system that starts from a CD-ROM. The purpose is nothing goes to the hard disk. APT is not possible because every time you start the computer, it's clean. Legbo Core, which are the guys that do a lot of research on EFI firmware, they have shown an attack from EFI, which is you boot from Tails, you assume you have a secure operating system, you are writing private emails, for example, you are a journalist or a whistleblower and trying to disclose information, and they show they can get the keys, the PGP keys, they can get you the password for the PGP keys. So the operating system Tails is not secure in this scenario. Once again, we are attacking from hardware to software. The software cannot guarantee that it's safe, even if it's booting from a CD-ROM or something that is with only. Some other attacks, you can attack the bootloader. This is something that you saw in Windows with the TDLR branch, the TDLR 3 and 4, for example, or very old viruses in the BIOS times. You would attack the BIOS and put something there. This is very simple, this one. You can put SMM backdoors. There's the very interesting post from that Russian researcher, Crash, about installing SMM backdoors. SMM is a privilege level on your CPU, very interesting. If you can run code there, you can control the whole machine. So this is very interesting to put rootkits. Hopefully I have convinced you with this that if you control EFI, your computer is under the control of the attacker. You cannot do anything from software. You have to search, or you have to guarantee the integrity at hardware level. This is why EFI is very important, or the security of EFI is important. Well, let me go briefly above around a zero-day story. So 2 months ago, or 3 months ago, or in May, I woke up probably not in a very good mood and decided to release a 0-day. The thing is, it was an accidental 0-day because I didn't know it was a 0-day. I assumed that Apple knew about the bug because there was the Thunderstrike presentation at Black Hat, and I assumed, okay, they disclosed, they know the bug. There is no problem in disclosing, and it made the whole confusion, made headlines on a bunch of newspapers and websites, which is basically a bug that allows you to control the firmware of the Macs. You can read on that website, on my blog, the whole description about this. I will just go very fast on that. What happens is, the operating system, you have the operating system, you have the EFI, they are at different levels. And if you can write from the operating system to the flash, your computer is basically has a very severe security problem. And this is what happened with this bug and with Apple. There was a way to write to the firmware from the software. The advantage of this is that, for example, you have a Safari bug, a remote code execution bug on the browser. You can start there. The user goes to a website. The exploit is executed. And then you continue to go down. You install a rootkit, or you just come to root. And then you write to a flash. You write to the flash, meaning you install an EFI rootkit. So if you install an EFI rootkit, you control that machine as long as you want, because probably no one will search rootkits there. This bug was very similar to Thunderstrike if you follow Mac security issues. Thunderstrike was presented in 2014 at CCCC, which was basically an attack with a pen with a Thunderbolt adapter. So this is one of the reasons why when someone offers to hey, you can use mine you never used because this is very interesting for installing rootkits. The difference is that rootkits, that the Thunderstrike, you need to plug in this. So this is physical attack, and my bug was a remote attack, or it could be triggered as a remote attack, which is way more powerful because I don't need physical access to your computer. The funny thing is that in 2002 and 2012, Snare was writing this on his presentation. He was writing that he could write from the operating system to the flash. And this is the reason why the Core 2 Duo machines, or everything older than Sandy Bridge, is vulnerable, because those machines don't have any flash protections. Intel developed those protections on the Sandy Bridge chipsets. So those machines, if you have access, if you still use one of those machines, a remote attacker can put an EFI rootkit on your machine easily. So don't use those machines. The bug was very simple to trigger. You just need to put your computer to sleep or force it to sleep. When you woke up the computer, it will be in a vulnerable state. This was one of the reasons why the bug was very funny and created a bit of a mess in the media and with Apple, because it was very simple. You don't need complicated exploit, you just need to put your machine to sleep. I found this when I was researching. I started with EFI because I had a computer that was locked. I couldn't remember the password, and I found this bug while doing some research there. As I told you, the Core 2 Duo machines are vulnerable. The only machines that are vulnerable, or the only Macs that were vulnerable, were this one, Sandy Bridge and Ivy Bridge. This was funny, and this was one of the reasons why I released the bug, because the newer versions weren't vulnerable. What happened is that Apple patched the bug by luck. They didn't know the bug was there. They just patched by luck, probably because Intel gives reference code to the developers, and the bug was fixed there, and Apple ported the fix, and that's it. You have updates available for all this. Apple fixed the bug 3 weeks later, so you probably, if you install some new version of macOS or the latest updates, your computers are not vulnerable anymore. If you didn't install, you should install, because the bug, as I've shown you, is very easy to exploit. If you are interested in details about reversing, then I wrote a second post with a lot of reversing details, which is basically a complement to this presentation. A lot more details, a lot more technical. If this presentation isn't already technical, go there if you are interested in this. I explain you how to understand the bug, how to create your own fix. So it's a very interesting post in terms of that. I also put all the relevant documentation, or the basic documentation that you need, because EFI standards are like thousands of pages, manuals like with thousands of pages, so it's a lot of stuff to read. If you read those, or if you skim through on those manuals that I have there, you'll know the basics of EFI. There were more bugs that were already patched, that are finally already patched. They were the same type of bugs that allow you to write to the flash from the operating system. This was presented by the Legbacore guys, the guys that do a lot of research on this. These bugs are finally fixed. Apple released a new patch last week, because there were more bugs presented in Thunderstrike 2 at Black Hat. There were still, Apple didn't patch yet those bugs, but finally last week they released this. So this slide is not updated. The Legbacore's guys were saying this one, which was mine and theirs, was patched, and there was a bunch of vulnerable bugs that weren't yet patched, but Apple finally patched those bugs. They had a very interesting slide from their presentation where they complained that Apple wasn't fast enough fixing the bugs. I finally talked to Apple about my bug. They did a lot of hard work fixing the bugs. The thing is that you can discuss that I made a very responsible or not thing in disclosing the 0 day. The thing is that they fix the bug really fast. And my position is that Apple doesn't like when they have bad publicity, and they react faster when something is against them, when they get bad publicity. So this is the same slide from last year. I know a lot of people on Apple, but I still tell them a lot of times that they don't know what they are doing most of the time. Hopefully they will improve their quality, their secret quality. So all of this was really to convince you, or until now, to convince you the importance of EFI. Now let's go into EFI. What do you need to know the basics? So if you want to go into EFI, you don't need to spend 1 month, 2 months to learn the basics, or I'm giving you the most important things that I think. So if you want, you can go home, get the slides if the conference publishes them today, and start learning EFI, start working with it, and don't need to know all the basics or the small problems that I had to go through. The first thing is, where is the chip? We need access to the chip. The chip usually is something like this. You can find it in your computer. You have to search. You have to open and search for the chip. It's usually a CMOS, serial flash. These are the two most popular chips in the Sandy Bridge and Ivy Bridge models. It's the chip doesn't matter. You can find usually the specs on the manufacturer websites, so it's not a big problem. The interesting detail, they are all SPI. SPI is a serial protocol to talk to the chips. If you are an hardware person, you probably know. And this protocol, it's very easy. It's 8 pins that you need to connect, or usually you don't need the write protection and the reset. So it's very easy to talk, and in terms of programming and the code that you need to talk, it's not very difficult. So it's a very interesting protocol to read the contents of the chips that support. Most of the chips are 8 megabytes in size. For these machines, for older machines, the Core 2 Duo, you have 2 megabytes and something else. You can also find some that are 16 megabytes in size on newer machines, depends on the model. This is also another chip on the newer machines, the WinBond version. This is probably Apple just doing sourcing. They got a better price from these guys and got the chips from them. This is all the list from all the chips that you will find on Macs. Might be updated with new versions, but nothing very important. An important detail for us. Most of the chips are 8-pin SOIC, which is the format on that picture. But new machines are starting to use this, SMD or BGA. BGA is with the small pins that underside. This brings a problem because with the SOIC you just need test clips or a probe, a clip, which you plug into the chip, and you are connected to the chip. With SMD, it's soldered, so you cannot usually connect a probe. And BGA is even worse because they are underside. They are not soldered, or they could be. They are on the small balls, and they sit there. The problem is, if we want to access those chips, we need to desolder those chips. So this is a potentially destructive process on accessing the chip. For example, if you want to do like I do, if you want to dump before you travel, if you you have one of these versions, it's very complicated to do that because I can destroy the computer. And these are some of the models that I think are using the SMD or BGA because I don't have these computers, but I was seeing pictures and I cannot find the SOIC chip on those. If you want to do experiments, you can buy this from AliExpress. You probably have the same better access to electronics in Japan than I have in Portugal. But they are very easy to buy from this. They are cheap enough. So if you want to do experiments, testing your code instead going on the chip, on the machine chip, you can buy them and that's it. Important thing. So I have shown you what is the chip, where it is, how it looks. Now, where it is inside the machine, because you have to know where it is. The Rutina model, like mine, the Rutina 15 Is, has the easiest access. You just disassemble it and the chip is there. Other Macintoshes or other Macs are very difficult. You need to disassemble the whole machine because usually they are underside the machine. But I have this machine, which is a Mac Pro 8.1, an older machine. And with some practice, I already can disassemble the machine in 5 minutes. So for example, half an hour is enough time to go to your room, to your hotel room, open the machine, disassemble everything, install a rootkit directly, assemble again, and leave everything. So it depends a lot on the machine. Let me show you some pictures. So this is the Rutina model that I talk about. You just remove the underside cover, and you have here the chip. This is the power where the battery is connected to, and the chip is there. You just plug in, and very easy to access. This is a MacBook Air. Doesn't matter the model. The chip is always on underside the motherboard, so you need to disassemble the whole machine, extract the motherboard, and then you finally have access to the chip. Mac Mini the same. The Mac Mini is very compact, so you need to disassemble everything again and access the chip. The Mac Pro, the one that is run the trash can, is also very complicated. You need to disassemble the whole machine to finally access the chip. If you do that, be careful with these connectors. They are you need to put some strength on them to connect back. I know this because I bought one of these computers, or the company sent me one of these. And the first thing I did was open and dump the flash. I was curious to see if someone would install a rootkit on my machine. I don't think so. And then when I connect these things, the computer goes red. And I was thinking, okay, I just destroyed a $5,000 computer because I wanted to access the chip. The reason was that this cable wasn't well plugged. Last, this is one of my motherboards, and you can see, what you can see here is that this is the chips. It has dual chips. And the thing is that Gigabyte put the cooler. This is the chipset cooler. Put the cooler on top of the chips. So what I need to do, I need to bend the pins of the cooler to access the chips. The case here, it's not always easy to access the chips. So this presents a problem, for example, at a company. You cannot be disassembling people's computers all the time to access the chip. Next point, we know where is the chip. What we need to know now, or what we want to do, is to extract the contents of the chip. There are two ways. Hardware, which is connecting the test clips to the chip. This is why I was showing you where the chip was, because this is the only way, the only reliable way to find if there's a rootkit. This is a trustable, as I told you, it's trustable method. The chip is disconnected, the chip has no power, you are the one supplying power. So you are asking the chip, give me your contents, and the chip will give you your contents. I'm not sure, I'm not an hardware guy. The only way to make this not work would be to install a rootkit inside the chip, inside the serial protocol, and somehow the chip would lie to you. I doubt this is possible, at least on this type of chips. So this is at least the best method we can use. For software, you can use some software, talk to the chip. Software is able to talk to the chip, but hopefully I convinced you that this is not very trustable, because if the machine has a rootkit, it can modify your software and tell you, no, there's no rootkit here, you are not looking at anything, nothing here, everything is okay. So this cannot work. This is good for experiments, but it's not good to chase EFI rootkits. What you need in hardware, you need something that talks SPI, the protocol. You have a list of programmers that are able to do this. You can get an FTDI chip, the 32H that does this. I use this version from Tramelodson, the author of Thunderstrike. The reason is that it works. If it does the job, it's easy to use. does the job. I don't care anymore about that problem. His flasher is based on the Teensy 2.0 and 3.0. He has two versions. Both work well. As you can see, it's very simple. This is the Teensy board, and this is the chip. He uses a test clip to connect to the chip. This is the easiest way because you don't need to connect every probe. It's very cheap to build. It costs you like $30. If you buy a Chinese clone, it's even cheaper. Doesn't matter much. It's very simple, so you can be okay with a clone. Not a big problem. Its biggest advantage is that it dumps the whole contents in 8 megabits. I tried to do some research on EFI like 2 or 3 years ago, and the only thing I had was a bus pirate. The problem is that the bus pirate takes 4 hours to dump an 8 megabyte, 64 megabit or 8 megabyte flash. This is not feasible if you are doing research. Waiting 4 hours for something to finish, it's not good to do research. This is why I like this version. It's fast. 8 minutes is good enough for this purpose. Let me just skip this stuff. This is for your reference. This is the pinout of an SPI chip. Usually you need to check with the data sheet if it's there, if it's the same, but most manufacturers follow this spec, these pins, so it shouldn't be a problem. If not, you can adapt to the chip, not very complicated. This is the layout on the Teensy, nothing very complicated. Solder there, solder to the chip, and you have your based SPI flasher. You can use it for read. Just a small detail. If you use the Teensy 2, its default voltage is 5 volts. The flash chips are all 3.3, so you need to put a voltage regulator. If you go to this website, it contains the part number, which is that one, MCP, and where to solder it. So it's 5-minute job or less to solder this, and it's okay. Some small tip and tricks. You might have some problems with the chip not working, not talking. One very basic trick is you just connect the write protect and the reset pins to the voltage pin. I don't know why this works. It works, so for me it's not a problem anymore. Last thing, you see some diagrams. Everyone calls the pins different names. I just left this for you. If you see different diagrams, they will use different names. So you have a small map to map the pins. How to read the flash? If you use the Teensy, you simply use the xmodem command, and you ask the chip to read the contents of the chip. You ask the Teensy to read the contents of the chip. 6 minutes, 7 minutes later, you have the contents. In this case, it's 8 megabytes ROM, and you can see it's here. This is a dump that I did before traveling to Korea. I dumped my ROM, so I have something to verify if someone attacked me, which would not be very smart. This is how to write. You connect to the program. You say, I want to write the whole chip, and then you send the image to the chip, and the Teensy will do the work for you and write the contents. This is some problems. Let me skip this. Not very important. Software. I will go just on the first one, on the first technique, to save time. The other ones, you also can use these too, but nothing very important. Something that you can easily do yourself. You need the flash ROM. This utility is a very known utility, open source utility, that is able to talk to many different types of chips, not just EFI chips or flash chips where the SPI is. You can use this, and this is a kernel extension that allows the machine to talk directly to the hardware. This kernel extension is not code signed, meaning that in theory you'll not be able to load on the latest macOS versions, but Apple whitelists this, so it still works with all versions except the latest one, El Capitan, because if you were here last year for my presentation, I used this to load rootkits into the system. This is an example how to dump with flash ROM. You just load the kernel extension, and then you use flash ROM and tell flash ROM dump the contents. You can see here flash ROM identifying the chip. In this case, it's Micron, one of the chips that I told you it's very common. It tells you some information about the chip, and then starts reading here, and then a few minutes. Usually it's very fast, so this was probably like 1 minute or something. You have the same contents of the chip. Then you can use this to analyze. This is the part I want to skip, something a different way to do it, but essentially it's by software, so same problems, nothing there. As I told you, software is good enough for experiments. If you are looking for, if you are doing incident response, software will not save you unless your rootkit is something like Hacking Team. Hacking Team was only interested in persistence, in keeping across reinstalls. They did nothing to hide the rootkit. So if you dump a machine that is infected with Hacking Team rootkit from software, you'll see the rootkit there. If you know me, I say a lot of bad things from a Hacking Team. If I was designing this rootkit, this would be the first thing I would work on. Just hide the rootkit, make yourself invisible to incident response. Next topic, what are the contents? You know where the chip is, you finally got its contents. Now what's in there, what do you need to look at? What are you looking at? This is one example of the content. You always see this. This is the descriptor region, which says the content is here, there, and there, and there, and there, this type of content. This is the Intel Management Engine contents. There was a presentation at the first Code Blue by Igor, which is a very big black box, a very interesting black box for rootkits. Igor is the only person in public doing research on this. I will talk about this in a bit. And then you have the BIOS region, which contains all the contents that we want to work for finding rootkits or reverse engineering. Another example of BIOS from a newer machine. Here you have the gigabit region, which is basically contents of onboard network cards. Intel, on their standard, says you can use the flash to put some data there, so they are using the flash for other stuff. Once again, the management engine region, and then you have another region here. I never explored the contents of this. It's irrelevant. It doesn't have. It's very small and it doesn't have anything interesting, at least from the manuals. But it serves to show you that you can see different contents in the BIOS. But this is something that you always see: the BIOS and the descriptor, and they are there for sure. A small image that shows you the contents of a BIOS. You can see the descriptor here, and this is the information about the descriptor. And then this is the contents of the BIOS files. A different dump that contains a different region, the platform region, the PDR region, just to show you the different examples. What is the descriptor? As I told you, it says contents are these. The BIOS region you can find at address X. The gigabit can be at address Zeta, and so on. It contains access permissions, meaning you don't want, for example, the network card to access the BIOS, because that would be an obvious way to make a rootkit. You attack the network card, and then from the network card, you attack the flash and install an EFI rootkit. So it guarantees that each region cannot talk to each other if you don't want. Intel Management Engine region. If you remember Igor's presentation, he told you that Intel Management Engine, it's basically a CPU inside your CPU. It runs there. The most surprising thing is that it runs Java. So your Intel CPU has Java running inside in parallel. And that's not very secure, or Java is the source of a lot of problems. it can be active when your machine is powered off, as long there is a battery inside the machine or a power source connected to it. That chip can do something. For example, it can talk to the network because that chip has an independent MAC address. This is used for administration. You have a big company, your machines are off, and you want to, for example, to boot them for launching updates or something. It's a very interesting feature. But the problem is that it can be a very powerful feature for attackers if they find vulnerabilities there. There is no access from BIOS and operating system. Unless you find a vulnerability, you can't talk to that. You don't know what is there. You cannot find what is running, what is happening there. As I told you, Igor made 3 presentations in different years. One of those presentations was at CodeBlue. This is an area that requires more research. People are talking about this again. Joanna Chotowska from the Blue Pill fame released a paper this week about, she says, x86 is insecure forever because you have Intel Management Engine, you have another stuff that is insecure or that we don't know what is running. Intel Management Engine is definitely something that we need more research on. These are the links for Igor presentations. You can read them or revisit again those presentations. BIOS region. The contents of the BIOS region, this is the one that we are working with on this presentation. It contains binaries, EFI binaries for different phases. I will show you in a brief what are these phases. It contains NVRAM, non-volatile RAM. For example, your Macs store the Wi-Fi password on this region. So if I find a way to dump the memory, or I can extract your Wi-Fi password and then crack it. This is one of the reasons why you format or you reinstall your Mac. After you reinstall, it knows your network because the information is saved there. It installs some CPU microcode. You'll not always see this in every models. It depends on the models. I guess if Intel releases a new version, then when there's an update, the microcode is there. If the CPU version doesn't have microcode, it's not there. Important thing, everything happens in a firmware volume. Firmware volume is a container for different data for the data on EFI. For example, the NVRAM is a firmware volume. Different binaries will be in different firmware volumes. This is a picture of my BIOS with different content. As you can see, each of these is a firmware volume. For example, this volume is microcode. This one is the non-volatile RAM. And this is where the machine starts booting from. What you can see here is that everything is a number and letters. This is called a Git. If you don't know this from Windows, it's a standard format, 180-bit characters format, basically to describe something. It should be unique. So everything in EFI is a Git. You don't have file names. You don't have something saying platform security.efi. Everything is a Git. This makes things a bit difficult to read because you don't have names on things. So when you are reverse engineering, you don't have any names. You have to do them. You have to translate that yourself. The content of most of those Gits you can find on the EFI specs. This is where you download all the manuals and then use the PDF search version to see. You find the Git and you want to know what it means. There are many Gits that are vendor-specific or private, meaning Apple has some Gits that doesn't publish. You don't know the meaning, so you need to reverse engineer to understand what they are doing. Or they are private. Some manufacturers publish their Gits. Others, they kept them private, and you only reverse engineering, you know, its contents. So Google and some luck are your friends in this case. If you can Google and it gives some hit, it will save you reverse engineering work. If not, you have to load IDA and fix things yourself. This is an example of a script that Snare created. What it does for IDA, what it does, it translates all the Gits to something to English that you can read, and this is one of your tools. You load the binary into IDA, execute the script. Hopefully it knows the gits and it will translate something to English. Your job will be much easier. Next step, the boot flow. What happens when you start your computer? This is the most famous chart in EFI. Almost every EFI presentation uses this one. What happens? This is the security phase. When you start your machine, this is the first phase. It tries to assure that everything is OK with the machine. So if everything is OK, you can continue in the process. Then you have the pay phase, which is pre-EFI initialization. This is a phase where it will start setting your machine ready for the next phases. For example, one of the most important tasks is to set memory. Your layout memory is different in different phases of the machine. This is one of the phases that takes care of setting memory for this phase, the DXE. This is the phase that takes longer time because it loads drivers that talk to the hardware. You can put, for example, an HTTP server here and so on. This is a phase that many things happen here. And then when this phase is over, you pass control to the bootloader. If it's in Linux, it can be grub or other loader. If it's a Windows machine, it passes control to the Windows bootloader, and so on. So at this phase, the operating system or the bootloader is starting to take control. So EFI is ending on this phase. And everything here is operating system stuff. As you can see, OS boot, and then you close your machine, and things start to shut down, and so on. As I told you, this is one of the most important. Set up memory for the DXE phase. This is one of the important tasks of the pay phase. This is another chart that shows you two boot paths. This is the normal one. When your computer is off and you start, it follows this one, the SEC, the pay, the DXE, and then the boot device. This phase is the sleep phase. This is where the bug that I disclosed was. So this is the phase, for example, when you put your computer to sleep, your computer does a bunch of stuff, puts some information in memory, and what happens is there is a script, and the reason for the script is if you had to execute the DXE phase all over again, it will take a lot of time for your machine to resume from sleep. There is a standard, I didn't know that, but I think it's like 6 seconds that it says your Windows or Mac OS, when it comes from sleep, it must take maximum 6 seconds to boot. So what they do is they save the information that they need in a script, and when you come back from the sleep, what happens is the SEC phase is executed, the pay phase is executed, but the DXE phase is not executed anymore because all the information is in a boot script. So you don't need to execute the drivers again. This is the reason why your computer is so fast coming up from sleep. Let me bypass this very quickly. You have many drivers inside the BIOS. How do you know the order of execution? There's basically one dispatcher in the pay phase and one dispatcher in the DXE phase. And you have dependencies between them, which is a very small language, a stack. There's a stack, you push there, and everything goes push and pop from there, and there's a Boolean logic there. And so this dispatcher knows what things or what the order things need to be loaded. Last phase, how to reverse EFI. You have the contents, you know what is there, you can access the contents, you can find the files. How do we start reversing? What is the critical information to start reversing EFI? These are the two tools, most important tools you can have on your toolset. This is snare scripts, the ones that reverse from GID to file names, very important, very useful. And this tool, UFI tool and UFI extract, allow you to extract the contents, very easy. You don't need to create your own utility. Those screenshots that I have with the contents come from this tool. It's a graphical tool, so it's a very nice tool. And these are the most critical tools you should have on your tool set. Important thing, I told you EFI has binaries, they execute. So what is the format? What is the format of the executable? The format, and is very, very, very funny because it's PE32 and PE32 plus or PE64. And you should know that these are the formats or the Windows format of the binaries. So you have the same format, the same binary format used on Windows being executed on EFI. It could be anything else. The format just says this is how do you execute, how are the contents. They opt out for PE. There is also another format, which is the terse executable. I will just explain on the next slide what is this. And you can find 16-bit, 32-bit, and 64-bit code inside EFI, depending on the phase. If you don't know, your computer still starts when you start your computer. It still runs in 16-bit. This comes from legacy. The first computers or the first Intel or some of the first were 16 bits. So your computer starts in 16 bits, then switches to 32 bits, and then the DXE phase is mostly 64 bits. So you need to reverse all this kind of code, all this kind of assembly, different assembly on your machines. TE, it's basically a version of PE, so nothing very complicated. What happened is that they've removed some headers that are not used for anything or they are not required. I guess it was to save space because the first BIOS or the first EFI, and they were 2 megabits, so you need to save space. You can find this format only on these phases, the sec and pay phases. Everything on the DXE phase is PE, so you only have trouble here. Very important detail, IDA is still unable to disassemble this format. So if you load these files into IDA, you'll all get very confused. IDA will get confused. The disassembly is incorrect. I had this problem and I couldn't understand, and then I finally start reversing the problem itself. And I found out it fails to parse the headers. As I told you, it's not fixed. The solution is you build your own loader. I released something here. So if you want to reverse these binaries, you just download my code, compile the plugin for IDA, and IDA can finally deal okay with these binaries. libc, or kernel 32 DLLs, if you come from Windows. You don't have libraries to link against. If you develop, you can, in Unix, you have libc. If you want to do a printf, it's on libc. If you want to do a message box A on Windows, you have another system32 or something like that. I don't reverse Windows binaries in 10 years or so. What happens is there are services. So instead of having a library that you link against, you have services. And what you say, I want to use that service. And services are nothing more than functions, or you can logically understand them as functions that you say, I want to use them. You get a function pointer for the function, and you can execute as a normal function. An example of a function in the pay phase, you can see there's a function to install a PPI. I will show you what is a PPI and other stuff. There's, for example, functions to allocate memory. So this is the basic functions, the basic set of functions that you have when you are in EFI. Some more example, let me go forward. How do you access these functions? You know the functions are somewhere, but you need to know how to access. What happens is that the entry point of an EFI binary, you always have a pointer to a table. In this case, this is the DXE phase. So you have a pointer to the system table. On the pay phase, you have a different pointer. This is the table, and you can see here are the 2 pointers to the services available on the DXE phase. So you'll see this type of code on the DXE binaries, which is basically it's making a local copy of the system table to a local pointer, the boot service table, and the runtime services. After you have these pointers, you know the offsets. The compiler will know the offsets when it compiles, and it can access the services from EFI. Functions. reverse engineering, you need to know the call convention, because if you see a call to some function or to some function pointer, if you don't know what is being passed, the order of the arguments, it will be very difficult to reverse engineer. The 32-bit binaries use the standard C convention, so everything is passed on the stack, nothing very complicated. As I told you, you find these in the sec and the pay phases. Don't ask me the 16-bit. I was reviewing the slides, and I don't remember the 16-bit because there's very few code running in 16 bits. This is an example where you can see everything, the stack, 0 on ESP being moved on the stack, normal code that you see reversing 32-bit binaries that use the stack convention there. The 64 bits use the Microsoft x64 call convention. So the first 4 arguments, first 4 parameters are passed on registers, and everything else on the stack. The core difference, and the first time you see EFI binaries of this kind, you'll get confused because there's a shadow space of 32 bytes on the function. It's very easy to understand this with an example. You have here a service being called, and you see the first 4 parameters being used on the registers, as expected. And then you see the 5th parameter like this, 32 bytes ahead on the stack. The first time you see this, you see where are the other arguments, because the 32 bits used on the stack normally. But the 64 version always uses 32 bytes. As long as you know this, there's no problem. You know that 32 bytes is the 5th parameter. In this case, it's 64, 8 bytes ahead, the next parameter. So very easy to understand. Protocols and PPIs, last thing on this. As I told you, there are basic services, so that those services don't allow you to do a lot of things. But EFI is very modular, and protocols and PPIs, it's what make it modular. What happens is you can put a binary that makes more services available. For example, you want to put a message to a log function. EFI doesn't have that. What happens is you create an EFI binary that will make a function to make logs available. So what you do, you create that function. You have to attribute a GID, because GIDs are like everything is going to be found in BIOS. And you publish that service. Everyone that wants to use this service basically needs to look up if that service is available. If it's available, you can use it. You get a function pointer, you can use that. There's a distinction between protocols and PPIs. They have a different name. I'm not sure why, probably because they are in different phases. The protocols are on DXC and PPIs on the pay phase. In practice, you can say they are the same. Services, the protocols and PPIs are nothing more than a GID identifies what is the protocol, and then they contain function pointers and maybe some data. Very quick example, I'm running out of time. This is the protocol. It has a GID. It says the EFI ACPI S3 save is this GID. So you always know that if you call this GID, you are calling this protocol. Then you have the definition of the protocol with 2 functions, the S3 save and the get legacy memory sizes. These are the 2 functions that this protocol implements. And then you have the prototypes of each function. You know this, you find this GID, and you can use this service. Let me skip this. This is how you use the protocols. First, you locate the GID, and then you use it. If you have a valid function pointer, you can simply use the service or the function pointer that you got. Let me go over this. Also, I will run really out of time. This is very self-explaining. Apple made some customizations to EFI. If you have some doubts about this, email me. But it's very easy to understand, hopefully. But if contact me if you have problems here, else I will have no time. Last part, how to find the monsters. We can access the contents. We know where the contents. We can dump everything. What we want now is some techniques to find potential rootkits in EFI. The two most important phases: dump the flash contents, because we need to get the data from the flash chip, always from hardware. Hopefully, I make a very strong case why hardware is necessary. And then you need something to compare with. Technically, you don't need, because you can reverse every binary. You have like 200 or 300 binaries inside your EFI. So that will take like a couple of months. Even if you are a very good reverse engineer, it will take a lot of time. The best way is have something to compare against. You can do like I do, dump before you travel, or have something that you assume it's OK. Or you can use updates that Apple released to compare against, because in theory, Apple, those updates will be OK. They will not be attacked too. You can find the updates from Apple. Apple has publishes updates for firmware. For example, to fix my bug, they had to publish an update. You can access on this URL most of the updates, or you can extract them when, for example, a new version, El Capitan, had some firmware updates, some EFI updates. Last week, Apple released also new firmware updates, so you can extract from them. Apple doesn't publish the hashes of those updates. I'm trying to convince them to do this, so we can verify if everything is legit. These updates are only useful for machines that have them. For example, if there's a new machine without updates, you don't have an update to download, so you cannot compare anything against. Either you assume that the machine has never been tampered with. For example, I opened my Mac Pro because I assumed it could be tampered. It stayed like a few days in the United States and then 3 days more in Germany. Probably too much time, and I assumed this machine might be compromised. So this creates a problem in terms of how to do this if the machine is very new. One solution is wait for an update, and then you can compare. I published, if you trust me, I published on my GitHub everything. I was looking for every firmware that exists, and I put there. I signed those firmwares with my PGP key. So it means that my reputation is at stake. If I put a rootkit here on this, and if someone finds it, my reputation will be, it will be very bad for my reputation. So everything is extracted from available updates. I did my best to guarantee that they are legit, that they are not tampered with. Soon I will put the SMC updates there. So it's probably a very good reference. If you don't want to chase or to download yourself, you can go there and you have all updates available there. Let me skip this. One of the updates formats is this. SCAP is a standard format. What you can do, you extract the contents of these updates, and you then compare with. These are the contents. You have a different grid. For example, you have the EFI capsule as a capsule has some contents, and then the contents that you want to compare with are inside another volume. So this is what I try to show you. There's a firmware volume, and then different contents are there. On one, you have the non-volatile region. On two, you have microcode, and 3 bit volume, and then it continues. So it's not a direct comparison. You have to process the update file and find the information, and then you can start comparing your contents. Techniques to find the rootkits. You extract, you dump the EFI content, and then you compare against the SCAP. Easiest way, you start locating all the binaries and start comparing one by one. You have one-to-many match, so it doesn't take that much time. Computers are very fast. You check sum against. If something is different, it's very suspicious. You have to analyze manually. It's the point where you start reversing the binaries. Things that you need to do. You need to verify if the contents have been tampered, but you also are interested to see if there are new files, because there are 2 ways to put a rootkit. Either you modify something or you install a new file. You'll also be interested, for example, to see if there are any missing files. imagine some EFI binary that creates a protection, and you extract the protection, and you get a backdoor. You also want to analyze all the free and padding space. That would be what I would use to put rootkit data. Instead of putting a new file, I would try to hide in the free space, and then the rootkit will try to find that data, encrypt it or somehow. So always verify this data because it could have interesting data there. Also verify the non-volatile RAM contents. For example, the boot device where the boot loader is located is stored there, so you could modify the path on boot there. Hacking team, for example, have to understand if they wanted to reinstall the rootkit, they put a variable there. So an easy way to detect hacking team is to see if that variable exists in the NVRAM. And this is, for example, the code from hacking team. What you can see is that they were doing this function, get variable, to read, is the variable there? If the variable is 1, we need to infect the system, or 0, we need to infect the system again. If the system is already infected, we don't need to do anything. Let me skip past these conclusions very fast. EFI rootkits or UEFI rootkits aren't unicorns. Not many people talk about them. I have no doubt they exist. Hacking team developed one. We know they are very rare. There are not many samples from this. But my thing is this, and some presentations talked about this. TT talked briefly about this. We don't know what's out there. TT talked about most virus, antivirus vendors. They have the samples. They can find the samples that they know about. But what you don't know about, it brings a very big problem. Especially if no one is looking for EFI rootkits, I can detect my machines, but without enough samples, we cannot be sure that there are not EFI rootkits or not out there. This is one of the reasons for this presentation, is to get people to start dumping their contents, to start searching for these kind of rootkits, to see if they are really out there, and what is their quality, what is their techniques, and so on. So don't assume that they don't exist. This creates a very big problem. Chasing these type of rootkits requires hardware. So you need, in most cases, to disassemble computers. And for example, in a large enterprise, I don't see a big Japanese enterprise with a big building, everyone going there to open the computer once a month or twice a month or whatever, disassemble everything to dump manually. This is not feasible. This is not scalable. So this brings a big problem at enterprise level. I don't know what is the solution. Vendors or hardware vendors need to start thinking about this, because this is important. An enterprise can be attacked with this kind of rootkit, and then they will have serious APT, not APT at software level, but APT at hardware level. And hopefully, I have convinced you that this is really interesting stuff, and it will stay on the company for a long time. Other problems in EFI, the vendors are very slow to release updates. For example, my that gigabyte motherboard is fully vulnerable. It doesn't use any protections. There are no updates, no firmware updates in terms of security. Most of the vendors, you will land in this situation. It's a bit like Android. They release the phone or they release the computer. They don't care about updates. So you have a problem, because if there's a bug there, you don't have any updates you could try to fix yourself. Let me pass this. Very last thing, this was some pictures. If you follow the Guardian case and Snowden case, the Secret Service's GCHQ from the UK demanded to destroy their computer. The funny thing is that they destroyed a bunch of chips. And the main question is, are those chips that they destroyed interesting for rootkits? What was the reason why they destroyed? They could destroy them because they wanted to just troll people. They're saying, yeah, we are destroying everything because we are going to cause fear. Or they really know more about those chips. So this brings interesting research questions. If you want research topics for next year, for present, start looking at this stuff, at these chips. You'll see on the slides there's SMC, there's Intel management, also very interesting. So start looking at this stuff. You can find from China boards, and they steal all the logic board diagrams. If you go see these diagrams, you can see a lot of interconnection between chips and CPU and interesting buzz. So there's a lot of interesting research topics in the connection between hardware and software. We need this. I'm trying to make the case with many vendors, or at least Apple. We need to trust the hardware. If we don't trust the hardware, if I don't know if my computer, the hardware has been tampered with, and more and more you have more chips in your computers. For example, the chip in the trackpad is an ARM32 chip, which is very powerful these days. So you can put a rootkit there. Imagine the trackpad is connected to some buzz that others interesting stuff goes there. You can do a lot of things from the trackpad. This doesn't make any sense. So many people, for example, AV, I'm a bit guilty because I'm next-gen AV. I'm trying to solve software problems when I cannot guarantee that the hardware is trustable. This is a big problem, and we need to start thinking in different terms. We need to start building the security from hardware to software instead of trying to do like now from software to hardware. One of the solutions is to put physical protections. If you are from the old times, there was a physical switch where when you wanted to update, you had to put the flash to writable. We lost that. We have no switches for cameras, for example. We have no switches for the mic in your computer. All my machines have physically disabled the mic. I have to open the machine and disable the connection. I do the same for the cameras. This shouldn't be like this. We should have some kind of solution to disable this. This is a computer, very fast. This is a Chromebook that it contains that solution. There's a screw here that you can, lock, and the machine will not be able to write to the BIOS. So it's a solution, hardware solution, to not let the machine, to not let the BIOS be attacked. Hold on. So hopefully, super overtime, hopefully I have convinced you that firmware security is very critical. We need more people to research on this. We need vendors to start thinking about this. I had some vendors, some people in China where I presented this last year, wanting to think about this, interested in this topic, which is good. Hopefully there are people here that are interested into this and will go back to their companies and try to start some thread to start thinking about that firmware, that's how important it is to guarantee the quality of your computers. If you need to contact me, you have the blog, you have the email, you have the GitHub where I publish all kinds of code. Feel free to contact me. I will try to help you as much as I can. And that's it.
テーラブラスさん、ありがとうございました。これをもちまして本日トラック2の最終セッションを終了とさせていただきます。